Welcome to Think, Build, Scale, a podcast that disrupts conventional consulting businesses. Because in this podcast, you get a lot more than your typical consultant and all of that for free. All you need to provide is some time and attention, which of course is the most valuable asset for an entrepreneur or a high value professional. Hence, if you are new to this podcast, I want to explain the flow of the episodes. Each month, a new topic will be discussed. This month, it is hydrogen automotives. Each topic will contain 3 episodes. This particular one is the second episode for hydrogen automotives. The second episode is all about building the product, which is, in this case, the hydrogen automotive. Now, before I go ahead, I want to bring to your attention that no company secrets or confidentiality agreements have been or will be violated consciously while recording the episodes of this podcast. Everything presented here is an amalgamation of knowledge and experiences from various industries and trainings I have had so far. The information presented here, to the best of my knowledge, does not overlap any confidential information that would fall within the trade secrets of any of the companies that I have had a non-disclosure agreement with. System architecture for development of a commercial hydrogen automotive. You have the architecture in 4 layers, or I would call them 4 different subsystems: the energy system, the powertrain and drive layer, or the powertrain and drive subsystem, the software and control subsystem, and then the connectivity and user experience subsystem. The development and testing roadmap for hydrogen-based automobiles is that you have in different phases. Phase 1 will be R&D and feasibility studies that generally goes for 6 to 12 months, tech feasibility and market research, prototype hydrogen fuel cell integration, and then phase 2 would be a prototype development itself, and that should be 12 to 18 months. Here you build alpha H2V prototype, that is hydrogen to vehicle prototype, and then you build hydrogen powertrain and tank safety validation tests. And then, of course, your software and integration and controlled testing. This is in phase 2, and it would take you around 1.5 years. Phase 3, testing and optimization. This is going to take you around 18 to 24 months. Crash tests, hydrogen safety compliances, range efficiency and fuel economy trials. Yes, it's going to cost you a lot of time. Phase 4 is your pre-production and certification. This is going to take you around 3 years. This is like 24 to 36 months. You have to look at regulatory approval and homologation, and you have to look at your manufacturing supply chain setup. Generally, what happens in automotive is that if you are a automotive company, provide the system architecture of your system and the requirements of your system to various different suppliers of yours, and they generally provide various different components. So the earlier you start and the more work you do in phase 1, you will have better results in phases 2 and 3 and 4 and 5. And ultimately, you will have better results in launching your product in the market. All right. After phase 4 comes phase 5, where you have mass production and deployment. This is definitely going to take you more than 3 years. Commercial launch and infrastructure support needs to be paid attention to. Expansion of hydrogen refueling network partnerships, and then infrastructure and ecosystem development for your refueling stations. You have to partner up with various different providers, and I talked about partnerships in the first episode itself. Why is it important to leverage infrastructure of your partners and not do everything on your own? I mentioned that in the first episode. Please go and have a look or listen to that episode of the podcast. For infrastructure and ecosystem, you also would need support for hydrogen generation and storage, even at home of consumers. So at home hydrogen generation and storage, you even have to think that far. So this is not an easy task, and you really have to manage several different stakeholders. Supply chain, electrolyzer manufacturers for green hydrogen sourcing, a hydrogen tank and fuel cell supply partnerships, government incentives and policies, collaboration with clean energy grants and incentives, your adherence to zero emission vehicle mandates. These are what will take a large amount of your time and brain capacity, I would say. This system architecture plan ensures a safe, efficient, and scalable hydrogen vehicle. It integrates advanced powertrain technologies, robust safety measures, smart software systems, and a strategic development roadmap to achieve commercial viability. So go to your screen again and look at it. You have phase one, where you have your R&D, and this is where you discuss your partnerships. This is where you look at the entire architecture of your project, what is needed, what is not needed. And you look at the tech feasibility of the existing technology. You look at your market studies. Phase two would be your prototype development phase. That's going to take 1.5 years if you really want to build a working prototype. Phase three is your testing and optimization, and that takes around 2 years. I mean, if we are lucky. Pre-production and certification phase will take around 3 years, and then mass production deployment will definitely take more than 3. So please follow a structured approach. Automotive is all about structure. Automotive is all about strategy, especially hydrogen automotives. These are high value capital equipment. Do not take decisions. Do not start working on a CAD model. Do not start working on your AutoCAD. Do not start working on without having a clear cut strategy on product development. So please do include consultants like myself or any other high value consultant that can truly help you develop a system architecture for your automotive components. When we were talking about the system architecture being split into 4 major subsystems, that is energies, subsystem, powertrain and drivetrain, subsystem, software and control and connectivity and user experience, subsystem. Today, at this stage now, I want to talk about energy system, subsystem. There are various different components within it. Component number 1 would be your fuel cell stack. Component number 2 is your hydrogen storage system. Component 3 is your battery pack or lithium ion or supercapacitor battery. Component 4 is your hydrogen supply system. Let's go back. In your fuel cell stack, the fuel cell stack in your energy system layer, it is a subsystem. I would call it a subsystem. The fuel cell stack is the heart of the hydrogen energy system. It converts hydrogen into electricity through an electrochemical reaction. So you have various different components like the fuel stack, proton exchange membrane fuel cell. You have the fuel cell control unit, you have the air compressor, you have humidifier, and your cooling system. Let's go through them step by step. Your your PEMFC, which is fuel cell stack proton exchange membrane fuel cell. It converts hydrogen and oxygen into electricity and water. Fuel cell stack proton exchange membrane fuel cell. This converts hydrogen and oxygen into electricity and water. Specifications are because every time you are developing an architecture, you always have to provide specifications for your various components. How do these specifications come from? Oftentimes you perform simulations, or you take the specifications from prior existing systems. You can also conduct hand calculations on them. So in this case, I have simply conducted certain, this is simply out of my prior knowledge. So here are some specifications for your PEMFC. Your power output should be 50 to 200 kilowatt. Your voltage should be around 250 volts to 800. Efficiency should be 50 to 60%, and operating temperature should be around 60 to 80. Your potential suppliers are Ballard Power, Plug Power, Toyota, Hyundai, and Nuvera. Your FCCU, which is Fuel Cell Control Unit, it manages fuel cell performance, efficiency, and durability. Specifications are that you need CAN bus, you need air and hydrogen flow regulations as your control algorithm. You can contact suppliers like Bosch, Ballard Power, Panasonic, AVL, and there are so many more. Feel free to give me a call so we can research together on this. Air compressor for oxygen supply delivers oxygen to the air compressor delivers oxygen to the fuel cell stack. The flow rate should be around 300 to 500 grams per second, and the pressure should be 2 to 3 bar. Your potential suppliers are Borg Warner, Garrett, Mahle, etc. Humidifier membrane. This is a humidification system. It maintains proper moisture levels for fuel cell membranes. Efficiency should be around 90% water recovery for these humidification systems. You have your potential suppliers like Parker Hannifin, your Ballard Power, etc. Cooling system. It regulates the fuel cell stack temperature. As I mentioned earlier, the operating temperature should be 60 to 80 degrees centigrade. Why? That is for effective proton exchange in your membrane. Beyond that, the membrane will degrade. So you have to regulate the fuel cell at a stack at a particular temperature, and you need a cooling system for it. The cooling type should be liquid cool. You can also look at nitrogen cooling systems, and you can also actually look at using high thermal conductivity materials. So there are various different ways to do it. I'm just giving you one path, that is the liquid cool system. Temperature range can be 60 to 80 degrees centigrade. That's the temperature that it should keep the system at. Your potential suppliers are Mahle, Valeo, and Bosch. Again, do not take my word for it. There are multiple other potential suppliers, small and big. Keep looking, keep doing research. You get confused, you can talk to me and you can come to me. Your hydrogen, here is an example of how your hydrogen fuel stack system can be. This is just an ideation. Hydrogen storage system. Hydrogen is stored in high pressure tanks and delivered to the fuel cell system. Hydrogen storage tanks, they generally should be made out of type 4 carbon fibers so that they are lightweight but durable. And carbon fiber, it simply means that you would need composites as their external shell. And type 4 carbon fiber seem to have worked quite well in the past. However, there might be problems with thermal management, but that's again up for the material experts to go deeper into. High tech capital equipment does not happen in one day. Everything takes time. Everything is a careful research topic. Okay, so your hydrogen storage tanks, type 4 carbon fiber tanks, they store compressed hydrogen gas at high pressure. And the pressure rating is generally 700 bar, and the capacity is 5 to 10 kilogram of hydrogen storage. Your carbon fiber composite with your material is generally a carbon fiber composite, as I mentioned before, with a polymer liner. I mentioned this before. Potential suppliers are Hexagon Purus, Toyota, Worthington Industries, and Faurecia. A refueling port and valve system allows controlled hydrogen refueling. Interface standard should be SAE J2601. Your refueling time should be less than 5 minutes. That's quite significant, by the way. WEH, Parker Hannifin, and Stobley are some of the potential suppliers you can contact. Pressure regulator reduces high pressure hydrogen to usable levels for fuel cells. Input pressure 700 bar, output pressure 5 to 10 bar. Bosch, Swagelok, Parker Hannifin, these are your potential suppliers. Tank safety valves burst and overpressure protection. They prevent excess pressure buildup and releases hydrogen safely. Activation pressure is 720 to 750 bar. Continental, Swagelok, Parker Hannifin are your potential suppliers. Let's take a look on how your hydrogen fuel cell and hydrogen storage tanks should look like. This is your hydrogen storage tank, and this is how the fuel cell should look like. Quite an interesting field of study. This itself could become one of the topics of my podcast. That is, I can make 3 episodes just on this slide, or I can write a whole book just on this slide. There is so much knowledge and information to be shared about this topic. So once again, you need more information and thorough consultation on this. Do not hesitate to write to me and reach out to me. Components, again, other components within energy system layer. So with your battery pack and hydrogen supply system, there are several different components within, whether it is a lithium ion or supercapacitor battery. You have a battery pack, you have a battery management system, and then you have regenerative braking controller system. The battery pack stores and supplies power to complement fuel cell. Specifications are 400 to 800 volt. Capacity is 1 to 30 kilowatt. Chemistry, you have the battery technology. I'm going to make a whole topic about it with 3 episodes on various different options available for battery for hydrogen automotives, as well as for your normal electronic vehicle automotives. Okay. Your potential supplier for battery pack, there are many. You have LG Chem, you have Panasonic, you have CATL, Maxwell Technologies, etc., etc. And battery management system, you can contact Bosch, Continental, and Texas Instruments. Generally, you need a CAN bus for communication, and you need a state of charge and state of health monitoring features for this management system. This goes more towards embedded system and software. So be aware of it, that it's not completely hardware, although your battery pack has to be compatible with your battery management system. A regenerative braking controller. It captures kinetic energy and converts to electricity. Its efficiency should be 70 to 80% energy recovery, and your max power is 30 to 100 kilowatt. Potential suppliers are Bosch, ZF, and Continental. This is again an ideation, but yeah, you would need several different fuel cells that is being resupplied with hydrogen simultaneously. That's the only way the range of the vehicle would be increased. There you go. The hydrogen supply system. It ensures controlled delivery of hydrogen from storage tanks to the fuel cell stack. Hydrogen pressure, hydrogen injectors, they control hydrogen flow into the fuel cell. The operating pressure is 5 to 10 bars. Potential suppliers could be Bosch, Continental, Parker Hannifin. Flow regulators and sensors, they ensure precise hydrogen flow based on demand. Accuracy would be plus minus 2% flow rate measurements. Honeywell, Parker, Hannifin, Swagelov, these are your potential suppliers. Hydrogen fuel lines, insulated piping, they carry hydrogen from tanks to fuel cells. Material could be stainless steel or composite, and your pressure rating is 500 bar. Swagelok, Parker Hannifin, these are your potential suppliers. Safety shutoff valves automatically stops hydrogen flow in case of leak or failure. The response time should be less than 1 second because it's a matter of safety. So an extremely accurate detection and reaction system. Bosch, Parker Hannifin, and Staubli are your potential suppliers for these, or at least partners who can co-develop with you. All right, let's go to the second important subsystem of the automobile system, which is your powertrain and drivetrain layer system, subsystem, electric motors. AC induction, electric motors convert electrical energy from the battery into mechanical energy to drive the wheels. Electric motor, AC induction or it converts electrical energy into mechanical power. You have a certain specification that will be needed, which is your power of 10 kilowatt to 100 kilowatt to 400 kilowatt, voltage of 400 to 800 volt, efficiency above 90%, and your cooling should be liquid cooling. Once again, cooling, it's a combination of using high thermal conductive materials, the geometry, and the cooling interface the cooling system that you choose. Liquid cooling is just one option. There are many more heat dissipation and heat sink designs that you can select. All right, your potential supplier here for your electric motor, whether it's AC induction or PMSM. It could be Tesla, it could be Siemens, Bosch, Nidec, Hitachi, Borg Warner, any of these. Single speed reduction gearbox. They transmit torque from motor to wheels while optimizing speed. Ratio 8.1 to 12.8:1 to 12:1. Material high strength steel, aluminum housing. Lubrication should be oil-based. Potential suppliers are Magna, Borg Warner, GKN, Dana. Motor mounts and housing provide structural support and reduces vibration. Material is aluminum or magnesium alloy. Potential suppliers are Custom Fabrication, Bosch, and Dana. You have power electronics as well. You have DC-DC converter, you have DC-AC inverter, onboard charger, and you have cooling system for your power electronics. For DC-DC converter, they steps down voltage from high voltage battery to 12 to 24 volt battery for auxiliary systems. And your DC-AC inverter converts DC power from battery to AC for your motor drive. Your onboard charger converts AC from grid to actually charge battery. And your cooling system keeps power electronics at an optimal temperature. I will not go too much into the specifications because these depend on the need of your vehicle and on the final system requirements. Visual listener, if you are listening, watching it in YouTube or even watching it in Spotify, you can see on your screen that the specifications of all of these components are listed. Take them as a guide. Do not consider them as the optimal and or the final number, please. Potential suppliers. You have Delphi, Continental, Valeo, Infineon for your DC-DC converter. For your DC-AC inverter, you have Tesla, Hitachi, Siemens, Bosch, Infineon, Mitsubishi Electric. For your onboard charger, you have Delta Electronics, BYD, ABB, Siemens, Delphi. Cooling system for power electronics, you have Valeo, Mahle, and Dana. Components within powertrain and drivetrain layer, a continuation of the topic. For regenerative braking system, which is a component within this subsystem, it recaptures energy lost during braking and converts it into usable power for the battery. So you have the brake control module. It controls energy recovery from braking. You have the motor control with regen mode. It converts braking energy into electrical power. You have high voltage battery interface that transfers captured energy back to the battery. And you have electro hydraulic brake system, which electronically controls brake force distribution. Potential suppliers for your regenerative brake controller or your brake control module are Bosch, ZF, Continental. For your brake energy recovery unit or motor controller unit with regen mode, You have Tesla, Bosch, Continental. High voltage battery interface, you can contact LG Chemicals, Panasonic, CATL, Samsung SDI. Electro-hydraulic brake system, you can contact Bosch, Brembo, and Continental. The specifications also are listed on your screen. Even if you're a podcast listener and listening to it while you're driving, you can always go back to this video and you can check out all of the specifications that I have mentioned for all of the components so far. All right. This picture here shows a braking system for regenerative braking. Once again, this is just a ideation. I want to let you guys know that the more you ideate and the more you strategize at the beginning of your project, at the beginning of the development, the easier it becomes to carry on with your mass production. Third primary subsystem, which is your software and control layer. So you have for your vehicle control unit, which is your software. It acts as the brain of the vehicle. It manages power flow, control logic, and communication between different subsystems. For your VCU, potential suppliers are Bosch, Continental, Renaissance, NVIDIA, NXP. Don't always look at them as potential supplier, but do look at them as potential partners, because they will have to customize the software as per your demands and your requirements, your market, and your users. Power management software, you can contact Bosch, AVL, Siemens. VCU firmware, you can contact Vector Informatic, ETAS, BlackBerry, yes, our BlackBerry, and Q. What do they do? So VCU firmware, the real-time operating system for seamless execution of vehicle functions. The power management software optimizes energy efficiency and power allocation. Your vehicle control unit, it controls power distribution between fuel cell, a battery, and electric motor. Your fuel cell control unit, which has three different components. Your FCCU, your unit itself, which manages hydrogen flow, temperature, and efficiency. Partners like Bosch, Ballard Power, AVL, Parker, Hannifin could be useful. Your hydrogen flow control software, it ensures precise control of hydrogen injection into the fuel cell. Bosch, Siemens, AVL. Hydrogen cell stack efficiency optimization software, it maximizes hydrogen to electric conversion efficiency. So Toyota, Ballard Power, Bosch, they are your potential suppliers. All right, some other software systems are thermal management systems and hydrogen safety management systems. On your screen, you can take a look at them. You have the thermal management control module, you have your coolant pump controller, battery cooling system controller, and your thermal system monitoring software. For hydrogen safety management, you have your hydrogen leak detector sensors, you have your emergency shutoff valve controller, and your hydrogen safety monitoring software itself. So on your screen, you will see the components, the description, the specifications, the high-level specifications, and your potential suppliers: Bosch, Mahle, Valeo, Dana, Continental, Parker Hannifin, Panasonic, LG Chem, CATL, Siemens, AVL, Honeywell, Figaro, Swaggerloff. These are all repeated, so please do take a look at what different suppliers it could happen that you go to Bosch and they are really able to produce a lot of 90% of your vehicle. It could happen that Continental is able to produce 30% of your vehicle. So it's all about going and having a discussion with them. If you need a good strategy on the architecture and strategy for how to approach these suppliers and to make them into potential partners, once again, hit me up. I'm there to help you and to strategize. Driver assistance system, once again, you have for autonomous emergency braking, for lane keeping assistance, for adaptive cruise control, hydrogen range estimation, and alert software. They're all within the ADAS, that is the Advanced Driver Assistant Systems. Additional supporting Components would be your vehicle connectivity module, your cybersecurity control unit, and your software middleware. Once again, all the potential suppliers and specifications, high-level specifications, are listed on your screen for you to have a good look at it. Software and control layer for hydrogen fuel vehicles. Once again, you have hydrogen safety regulation compliances that you have to take care of, and your fire and leak prevention safety systems. They have to go through real-time monitoring with emergency shutoff and controlled gas venting to mitigate risks. The safety is very important. So the hydrogen leak detection sensors, the automatic emergency shutoff valves, the venting system, and the flame arrestor and spark prevention system. These are extremely important. And big companies like Honeywell, Figaro, Bosch, Continental, Swageloff, Parker Hannifin, Hexagon, Purus, Staubli, Worthington, Continental, AVL, they are all working on these already. They could be potentially very good partners or suppliers for your vehicle. Crash safety. Hydrogen-powered vehicles must be equipped with impact resistant storage, emergency power cutoff systems, and crash test enclosures. Reinforced hydrogen tank enclosure, automatic emergency power cutoff, and the hydrogen tank burst disc, and crash-resistant high-pressure hydrogen fuel lines. So, reinforced hydrogen tank enclosure, it actually protects tanks from crash impact and punctures. Materials could be carbon fiber or Kevlar composite. Impact resistance should be up to a G crash rating. And of course, your Hexagon, Purus, Toyota, Faurecia, these are your potential suppliers. Automatic emergency power cutoff, it disconnects battery, fuel cell, and hydrogen supply in a crash. Activation time should be less than 50 microseconds. Trigger sensors should be in your accelerometer and pressure sensors. You have Bosch, Continental, and Aptiv who are actively working on it, so they could be your potential suppliers. When it comes to hydrogen tank burst disc, this prevents overpressure buildup during fire or crash. So your activation pressure should be around 750 bar, and the response time should be really immediate, which is like 0.1 milliseconds at best, I would say. Swagelock, Parker, Hannifin. So you need really accurate sensors. Swagelock, Parker, Hannifin, these are your potential suppliers. Crash-resistant high-pressure hydrogen fuel lines. Flexible, reinforced fuel lines prevent ruptures. Your stainless steel composite, your pressure rating, your stainless steel composite could be your material, and the pressure rating could be 700 bar. Swagelock, Parker Hannifin are your potential suppliers. Swagelock, most of these potential suppliers are just getting repeated, which means that you can really leverage one partner or one supplier for multiple parts, for perhaps even an entire subsystem of your car. So think about it. If you have like 4 major subsystems, then why not have 4 major partners who would build those subsystems, and all you do is make sure that the architecture is intact and the integration is validated properly. Think about that. Additional supporting components. You have your vehicle supply safety control module. It integrates hydrogen safety, crash response, and fire mitigation. Hydrogen storage pressure sensors monitors tank pressure in real time. Overheat detection sensors, they prevent thermal runaway in fuel cell and battery pack. Your post-crash hydrogen inerting system, it floods hydrogen storage with inert gas to prevent combustion. All of these, the specifications are listed right there, and potential suppliers are also listed. Have a look, and for more information and more understanding, write to me, and let's talk. Some of the additional systems to consider are your hydrogen telematics systems for cloud monitoring of fuel levels and predictive maintenance, your remote diagnostics and software updates, user interface and infotainment, your digital cockpit with real-time hydrogen economy display and integration with hydrogen refueling station locator, and your mobile app that would remotely monitor hydrogen levels and vehicle status. Trip planning could be based on such monitoring systems. All right, then safety and compliance. Hydrogen safety regulations. You have various different ISO standards, you have SAE, UNECE standards, and also you have fire and leak prevention valves that you need to take care of, and a venting system as well. For your crash safety, you need to have reinforced hydrogen tank enclosure and automatic energy emergency power. Cost, and cost. Cost is everything in the capital equipment industry. Therefore, strategy, and strategy is what is needed at the beginning phases of your product development process. Very, very important to remember this. Reducing the cost of a hydrogen powered vehicle requires a holistic approach, addressing fuel production, storage, vehicle design, manufacturing, supply chain, and market adoption. Here is a breakdown of key strategies. First is to lower hydrogen production costs. You need to scale green hydrogen production by investing in large-scale electrolysis using renewable energy like solar, wind to drive economies of scale. Improve electrolyzer efficiency. Example, solid oxide or PEM electrolyzers. Co-locate electrolyzers with renewable energy sources to avoid transmission losses. Explore nuclear-driven hydrogen production. These are high temperature electrolysis. And then cheaper blue hydrogen solutions. They enhance carbon capture and storage to make natural gas-based hydrogen more competitive. Optimize steam methane reforming efficiency. Decentralize hydrogen production. Develop on-site hydrogen generation at fueling stations to reduce transportation and cost and storage cost. When I'm talking about cost reduction, I'm really looking at the entire system of a hydrogen automotive. It's not only about one startup anymore. I'm really looking at all different ways that the overall cost of a hydrogen automotive can be reduced. So even though you are not in the field of hydrogen generation itself, be aware that your product is directly linked to the fueling infrastructure and the cost of generating hydrogen. Just remember that, and that's why listen to this segment that discusses the path to cost reduction. Reducing hydrogen storage and transportation cost. How do you do that? Better compression and liquefaction. You have to optimize liquid hydrogen storage to reduce boil-off losses. Use higher pressure storage tanks. For example, 700 bar instead of 350 bar. Alternative hydrogen carriers such as ammonia as a transport medium, which is easier to store than cracked into hydrogen on demand. Liquid organic hydrogen carriers, they're also called LOHCs, for safer low pressure transport. Lightweight hydrogen tanks, they develop carbon fiber reinforced polymer tanks with automated cost efficient production. Explore metal hydrides for solid state hydrogen storage. Cutting down vehicle production costs, it would be cheaper fuel cells, modular fuel cell design, hybrid powertrains, lightweight vehicle materials, and then manufacturing and supply chain optimization. For cheaper fuel cell, reduce platinum content in proton exchange membrane fuel cells, mass produce solid oxide fuel cells wherever it's suitable. Develop recyclable fuel cell stacks. Remember that recycling is one of the ways to truly bring down the cost. Modular fuel cell design. You could standardize components across multiple models to reduce R&D and production costs. utilize swappable fuel cell stacks for different vehicle sizes, integrates and now let's go to hydrogen powertrains. Integrate small battery packs to optimize power delivery, reducing fuel cell wear. Regenerative braking to recover energy. Lightweight vehicle materials like aluminum and composite materials for chassis and body. Aerodynamic optimizations to reduce drag and improve efficiency. Manufacturing and supply chain optimization. Mass production of fuel cells and hydrogen tanks. Shift from low volume production to automated mass production. Establish a global supply chain for critical materials like platinum, carbon composites. Encourage circular economy and recycling of materials. Localize supply chain, avoid reliance on expensive import components, invest in local fuel cell gigafactories, standardize hydrogen vehicle parts, design parts that can be used across multiple vehicle models and even different brands. Expand hydrogen infrastructure to lower costs, building more hydrogen refueling stations, deploy shared infrastructure between automotive, trucking, and industrial applications, encourage public-private partnerships to fund station rollout, hydrogen pipeline network, so integrate hydrogen transport into existing natural gas pipelines, develop regional hydrogen hubs to create high-demand clusters, government policies and incentives, subsidies for hydrogen vehicles and refueling stations, as much government subsidy as possible. Please make sure that you are utilizing those grants from the from your government. Mandate fleet transitions to hydrogen, carbon tax and fossil fuels, increasing cost on high emission alternatives, and then of course regulatory push for hydrogen adoption. Many countries are going towards zero emission vehicle, but of course the government has to support the companies and the consumers in order to adopt those regulations. You cannot just put a stop to transportation and the entire economy in one day. Increasing market demand to reduce costs. Hydrogen vehicles in commercial fleets focus on buses, trucks, forklifts, and heavy transport to drive initial demand. Large fleets require cost per vehicle via bulk production. Hydrogen-powered aviation and shipping. Cross-border adoption boosts investment in fuel cells and refueling infrastructure. Consumer awareness and incentives. Educate consumers on total cost of ownership, not just upfront costs. Offer hydrogen vehicle purchase and leasing subsidies. To low cost reduction is to make hydrogen vehicles affordable. The industry must simultaneously scale production, optimize supply chains, improve technology, and secure policy support. The biggest cost reductions will come from mass manufacturing, better hydrogen storage, cheaper fuel cells, and infrastructure development. You have to acknowledge the complexity of hydrogen automotives and why you don't see the ultra rich who can actually afford them at any price isn't showing them off in your poshest streets of your country. It's because of safety considerations and, of course, the practicality of refueling. So why hydrogen safety is more complex than your EVs? Hydrogen gas is highly flammable, requires higher and more sensitive sensors for leak detection, venting, and shutdown systems. You need high pressure storage. Unlike electric vehicles, 400 to 800 volt lithium ion batteries are used. Stores FCEVs, which are fuel cell electric vehicles, store compressed hydrogen at 700 bar, and therefore it requires reinforced fuel lines and crash-proof enclosures. Regulatory compliance. You have several ISO and SAE and UN ECE requirements to be taken care of for your certification and these things drive your hardware costs up to a significant amount. Cost and safety balance. So for entry-level FCEVs, the focus on leak detection, emergency shutoff, and crash resistance, that should be your priority when you're an entry-level FCEV. So this would go around 5,000 to 10,000 on your investment. For advanced FCEVs, you should have real-time hydrogen pressure monitoring, post-crash safety measures, and AI-driven safety diagnostics. This could go up to $20,000 of investment. And then for heavy FCVEs, like your hydrogen trucks, buses, etc., they really require additional explosion-proof measures, and they would definitely go, it could be around even 50,000 additional cost as your investment. Safety compliances. We talked about this in our previous segment as well, that you have your fire and explosive risks, you have your storage, pressure and containment, you have your leak detections, crash safety, post-crash systems, so many. So let's go step by step. How are FCEVs and EVs different? So your hydrogen compliant FCEVs, fuel cell electric vehicles, they have a higher risk due to high hydrogen gas, which is more flammable. But then you also have your thermal runaway. That is, your lithium ion battery gets overheated to a significant amount, and you need to ensure a proper cooling system for that as well. So both have their advantages and disadvantages. Storage, pressure, and containment. 700 bar hydrogen storage requires crash resistant tanks. Remember that it's really, really high pressure. And for your 400 to 800 volt batteries, they require reinforced enclosures. Leak detection, hydrogen leak sensors and auto shut-off valves are mandatory. That's a non-negotiable. Battery state monitoring for overheating is required in your normal EVs. Crash safety for your hydrogen tanks must withstand 100 G plus crash forces. Batteries, on the other hand, in your EVs should not rupture or short circuit. For hydrogen, you require post-crash inerting systems to prevent combustion. We talked about this earlier, where as soon as there is a crash detected, the entire fuel cell system would be filled with an inert gas, just so that the hydrogen explosion does not occur, and if it occurs, it is instantly neutralized. Some EVs use electrolyte cooling to prevent fires. And then for your refueling or charging safety, you have ISO mandates, so many other mandates, both for FCEVs and BEVs. Regulatory compliance complexity is always there. It's more complex in hydrogen, though, because of the way you have to handle hydrogen and high pressure storing. Your electric vehicles are significantly less complex, but requires robust thermal management. A regulatory breakdown in US, European Union, Japan, and China, they all have their focus area. US is focusing on hydrogen storage, refueling station compatibility, and crash protection. European Union is focusing also on crash safety, leak detection, and emergency shutdown systems. Japan is leading actually in hydrogen refueling safety and post-crash risk mitigation. China is focusing on high pressure containment, fire suppression, and safety redundancy. In general, post-crash hydrogen safety innovation, hydrogen safety compliance is more complex than EVs. We have already established that. But yeah, different components, different continents are leading this field in different manner. One thing to remember is that post-crash inserting systems will become mandatory in all major markets by 2030. Innovation. Whenever you are building a capital equipment, you always run into the need for innovation, because the demands of the market cannot always be met with existing pieces of technology or software. Fuel cell electric vehicles. In the table, you will see three major areas need investments in R&D. There are many other existing techs that could be actually borrowed from your standard electric vehicles that you have today. For example, your electric motor and drivetrains could be borrowed from your EVs. Your power electronics could be borrowed. It could be adapted with a little bit of optimization. Your driver assistance safety, it could be ditto copied, literally ditto copied. You don't need additional investment there. Your crash safety and chassis, you need a little bit of you can borrow from your EVs, but you need some adaptation as well. Fuel cell stack and power control, that will require major investments. Your hydrogen storage and leak prevention, that is going to require a lot of investment. And then your hydrogen refueling and infrastructure, that has to be developed from scratch, and that is a big investment. And I really hope and urge the governments of all continents to focus on to help companies, to help corporates build hydrogen refueling and infrastructure. It is not simply enough. It is not simply enough to say that, yes, we are going towards clean energy, but it is very important and vital that the government is partnering up with companies to build hydrogen refueling stations. All right. Hydrogen fuel stack and power control. Unlike an EV, where a power comes from a battery, an FCEV generates electricity in real time through a fuel cell reaction between hydrogen and oxygen. Optimizing fuel cell lifetime, catalyst efficiency, and cold start performance requires custom R&D. Catalyst materials you can reduce platinum dependency for catalyst materials, and this will improve the cost and the need for high investment. Improved membrane durability and AI-powered fuel cell stack management, that will help a lot. Your leading developers are Ballard Power, Toyota, Plug Power, and Hyundai. For hydrogen storage and safety systems, well, hydrogen is the smallest molecule and leaks easily. Gasoline and lithium ion batteries do not require ultra high pressure storage, but hydrogen does, and it requires sensitive detection and advanced containment strategies. Your investment areas are advanced composite tank materials, smart leak detection sensors, predictive failure algorithms, and your leading developers are Hexagon, Purus, Toyota, Worthington Industries, etc. Hydrogen refueling infrastructure. Like I mentioned before, government should help the corporate here. And yes, unlike EV charging, which follows standardized connectors like CCS, CHAdeMO, Tesla superchargers, your hydrogen refueling lacks universal standards. So companies must develop refueling station compatibility, and they should develop smart nozzles and pressure regulated fueling to ensure safety and efficiency. These nozzles should be standardized towards all vehicles. Therefore, a global structure is necessary for hydrogen automotives. It's not just one company doing one thing alone in their niche. Alone, you cannot walk in this industry. You really cannot walk. Companies must develop investment areas, high flow hydrogen dispensers, cryogenic hydrogen storage, and smart refueling algorithms. That's where your investment would go to. You have Air Liquide, Linde, Toyota, and Plug Power working on this already. There are several companies that are already working in these industries working in these areas that require high investment. So I already mentioned about them in my previous slide, but here is another slide again where Toyota is actually innovating in fuel cell stack and hydrogen power systems. Toyota Mirai's fuel cell, which is your fourth generation PEM FC. It's running at 60% efficiency. PEMFC is your protein membrane based fuel cells. All right, and then your Hyundai is working on Nexo SUV, on hydrogen trucks. They give up to 1,000-kilometer range. Ballard Power Systems, which are proton exchange membrane fuel cells for trucks and buses. Then you have your Plug Power that's working on hydrogen-powered forklifts and commercial vehicles. Bosch is working on fuel cell stacks with AI-driven efficiency models. Hexagon Purus is working on 700 bar. Worthington Industries are working on crash-proof hydrogen tanks for trucks and buses. R&D, Toyota is working on R&D on self-healing polymer materials for leak prevention. Bosch is working on real-time hydrogen leak detection with automatic shutdown. Air Liquide has been developing a global hydrogen refueling network. Siemens is working on high-efficiency PMSM motors for FCEVs. Bosch is working on hydrogen fuel cell compatible power electronics. Nidec is working on high-efficiency lightweight electric motors. Mitsubishi is working on silicon carbide based inverters for FCEV power management. Closing remark from my side: as we stand at the crossroads of a new era in clean transportation, the path forward for hydrogen fuel cell electric vehicles is clear. Innovation must be met with collaboration. The breakthroughs in fuel cells, hydrogen storage, and power electronics are redefining what's possible. But no company can build the future alone. Startups bring agility, scale-ups bring execution, established corporates bring resources. Together, they can fast-track the hydrogen revolution. For those looking to enter the FCEV market, the time to act is 2025. And the person you can go to for your first consultation is yours truly. Existing technology from industry pioneers, licensing proven solutions, and forming strategic partnerships, companies can accelerate development and reduce risk. Hydrogen mobility is no longer a distant vision. It's here, it's evolving, and it's ready for those bold enough to shape its future. Thank you for joining me in this deep dive into the FCEV architecture. The next episode is about how to scale your company that is working in development of hydrogen FCEV, and what are the different operational challenges you will face and how to tackle them.